Okay, so last time we were talking about Morse potentials, right? How you have two atoms that are held together by a bond. We'll call that the bond radius, right? And then as it stretches and compresses, we're going to model that based on a spring, right? So we're going to essentially use Hooke's law from physics to model our Morse potential. The Morse potential basically, you take the two atoms, you stretch them out until the bond breaks. Right, so you have your bond distance here, stretching the bond out until it breaks. Once it breaks, you can move them further and further apart, and it doesn't really change the energy all that much. On the other side, as you bring them together, they eventually get down to the bond distance. Then once you start pushing them together, you got the two nuclei repelling each other, and then the energy goes up. The general shape can be roughly modeled based on a parabola, right? You can see that it's not a perfect fit, but the parabola gives us a much better or much easier bit of math to do than what you would see actually trying to use the Morse potential. So how that plays into what we were doing, right? We use our wave equation. All right, so this is always going to be our starting point. The question is, what does that look like, right? What does the the H hat look like? So in this case, it's we're going to be using our standard minus h bar squared to, now for this one, you could use, if you have one that's way more massive than the other, like a chlorine hydrogen bond, right? You could just use the mass of the hydrogen, treat the chlorine as being stationary. In your book, it has 2m, but you can also do 2 mu, where the mu is the reduced mass, depending on if they're similar masses or if they're so vastly different that one of them doesn't really do any moving. M here becomes approximately what mu is anyways, right? So, and then, let's see, if we're looking at it just moving along R, we're going to specify that we're going to use x as being equal to essentially the displacement away from the bond distance, right? So the R naught is the bottom here. We're going to essentially just call that x0. And then however far it gets displaced, left or right, that's our x. So x is going to be equal to wherever it's at minus its resting place. So essentially that means that once the two atoms are their appropriate bond distance apart, x is equal to 0. And then you either stretch or compress it. What that will give us for us is our potential. If we express it in the x direction, would be equal to, so if we try to fit our harmonic, a parabola, to the Morse function, it's sunk down based on dE, which is the stability caused by bringing the two atoms together, right? So essentially, that would be, we're going to add dE onto the one that actually fits the Morse potential, and that would be V of R minus R naught, right? So we're going to add the dE onto it. What that'll do is it will shift the value from how much energy we get back from the two atoms coming together. It'll shift it up to the y equals 0, making the math a little bit easier to work with, right? So we're just doing a couple approximations to make the math easier to work with. Okay, so essentially your Vx is going to then be 1/2 some spring constant x squared, just realizing that whatever this function looked like, it's pushed up by d. Okay? So we're going to have second derivative with respect to x. We're just going to be looking at it along the x-axis of phi, of x plus, and then we have our v naught, right? So the Hamiltonian is the kinetic plus the potential. This time we actually have a potential, and the potential isn't straight vertical lines. So 1/2 kf x squared, and then that is multiplied by your wave function. That is going to be equal to e psi of x. All right. Now there's this particular setup where you have the second derivative of an equation times some other function of that same equation in terms of a eigenfunction. There's not a lot of solutions to that. In terms of differential equations, there are, in fact, they're known, and so we are not going to actually derive it. We're just going to say these are known, and we're going to use what is known that falls along with that particular type of equation. As long as everyone's A-okay with.
For the Vx? Or
No, coming up with ways of doing this. So we need to come up with a wave function that fits that pattern. It's a fairly restrictive pattern, right? So there's not a lot of functions that will do that you can take the second derivative of it and add x squared times some constant to it and get back a constant times the function, right? You're doing a whole bunch of stuff to the function, getting back the function times a constant. There's not a lot of things that that's going to work for, okay? So the equations that works for are called Hermite polynomials, right? In the Atkins book, the 11th edition, it's table 7E.1. In the other editions, you're just going to have to look through. If we're talking about the harmonic oscillator, there's going to be a table that will actually look. So this is the 8th edition, or sorry, the 10th edition. The table is going to look essentially like that, right? They essentially copy and paste it between different versions. I prefer using n to the new here for our, this is essentially the quantum or quantized number. I like just using n for most of them when I can, but they use new. Essentially the first, second, third, fourth, fifth, sixth state, and then if you're using 0, that's what the Hermite polynomial that goes along with an n of 0 gives you. If you use n equals 1, you get this one, n equals 2, 3, 4, 5, 6.
So at a given n, that's your psi of x?
No, that's what you plug in. Your psi of x is, so look for that equation. The way that you make psi of x is your psi for whichever one you're doing, you know, the particular quantum number of x is going to be equal to some normalization constant, and that normalization constant changes depending on which n you're selecting, right? So in the previous examples, the normalization constant was some function, right? For a particle in 1D box, it was 2 over L raised to the 1/2 power, and it was that for all boxes and all n values. This one, because we're going to be plugging in those Hermite polynomials, we need to have something that accounts for the different function every single time, and so your normalization constant will be different every single time. Okay, so we have a place to put our normalization constant. Your book uses h. Note there is no hat to it. This is not your h hat, right? That one depends on which n you select. And it's going to, instead of using x, it's going to use y. Some places when you look, there it uses chi, depending on the sources. I've seen this one's more frequent in physics texts, but your book uses y. So just putting that there so that you can write in your notes. If you're looking online at sources, you know why the examples from the lecture slides don't have the chi. I'm trying to be consistent with your book, but you might see this when you're looking at different sites. Okay, and that's e to the minus y squared over 2, right? So depending on what your n value is, you can go through and select the different Hermite polynomial. There's a general way of solving the n value, but it has your n 2 to the n here, and then n factorial, and so you have to plug in a different number, and so you get a different value. They're all going to be closely related, and I will be posting these lecture slides probably tomorrow. I'm almost done with them, finishing up like the last one. Okay, so the y, the key part here is that y is actually directly proportional to x. Right? Y is equal to x divided by alpha, and then alpha is essentially a bunch of constants. The mu is your reduced mass, kf is that force constant. So these two values are going to change depending on your system, but for a given system, they're the same. Okay, so you plug that in. Now, the Hermite polynomials, they have a couple properties that are going to help us out when using them. So, the vertical dash here on the h means the derivative. So, the second derivative of a particular n value for a Hermite polynomial is subtract that from 2y, where the y here is equal to that y, right? Times the first derivative of that same polynomial, plus 2n times the regular polynomial is equal to 0. We can use that to do some stuff. We're going to use this one a good bit more, where if you have an n value, one down on the table, minus the one that you're interested in using, or well, minus 2y times the one you're using, plus 2 times the n value that you're using, using the Hermite polynomial one above the particular line, right, is equal to 0. We use that to rearrange, solve stuff. It will help us cancel things out. We're actually going to use this one here in the derivation today. Okay. The last one is that if you have two different Hermite polynomials like n1 and n2, right? If you take the product of those times e raised to the y dy, if they are different lines, then the integral is going to equal 0. If they are the same line, then this is the result, right? And that value is going to change depending on your n. Okay, so they have very set rules or very set patterns that are going to help us use them. If you were to need this on a test, the table is going to be provided. There's no reason for you to memorize something like that you can easily look up.
And like the 3 last parts there? Like,
Yeah. Yeah. There. Some stuff that you'll need to, memorize, but not a whole bunch of stuff. Okay. So let's say we're interested in finding x, the average x and the average x squared. Right? So this is one of the things you want to be able to do for any of these systems. Right? So we're going to look for that one. We're also going to look eventually for x, the average of x squared. Right? So, as always, this is equal using Dirac notations. Okay, and we're going to use subscript n. Well, x is just x, and then n because we're going to be specifying which state we're going to be doing it in. Right? You have to, because in order to make your wave equation, you need to pick your n. We have to specify the average x value for which n are you talking about. They change between values. Yes?
Would the left wave function be like with a star?
In the Dirac notation, it isn't, but when we take the Dirac notation and put it into the integral form, it will. So the left one is the one that gets a star, the right one, so this is called the bra, that one's the ket. So the bra is the one that is the complex conjugate. But if you look at the wave equation, or what's going to be the wave equation, right, it's n, this n, there's no I anywhere in there. The Hermite polynomial, there's no n's in these, and if you look at the rest of the table, there's no I in any of those. E to the minus y, y is x over alpha, there's no I in alpha, and so while yes, it is the complex conjugate, there is no imaginary form in the equation, and so it doesn't actually matter.
So it just becomes like sine squared, right?
Yeah, it's essentially psi squared. Yeah. So this is equal, this is equal to the integral from our lower limit to our upper limit. So we're going to use negative infinity to infinity. Realistically, once the bond breaks, you're not really doing infinite distance, but it trails off down to 0 anyway, so we're not going to worry too much about that. Okay, so this would then be psi star x psi of x dx. Okay, now plugging in our general equation here. All right, we're going to just do this generally for any n. Now, before we do it, if we're looking at a spring, right, that stretches and compresses, the general motion of it is going to look like this, right? So the wave equation looks like that, where we have some sort of a symmetric. Essentially, it gets stretched and then compresses back. So you have your equilibrium state. You pull it out to stretch it, and then it oscillates back and forth between the two, spending equal time being stretched and equal time being compressed, right? So what we expect to see is that its average position is going to be in the middle, right? So its average position, half the time it spends being stretched, half the time it spends being compressed, and so when you average those out, it should come right in the middle.
Equilibrium.
Yeah, well, it will be the equilibrium position, yeah. So what we want to see to confirm that is that this should come out, our average x value should come out to be 0. The x squared is more weighted, because you're squaring it, the negative component turns positive, and so that's a way of seeing how much does it deviate from the center value, right? So if you're thinking about the average x position, where it's located at any given point in time, because it's a spring, it's going to be traveling through the center at a pretty good clip, right? So that's where all the potential energy has been converted into kinetic. Then when it gets compressed, it slows down, goes the other way, stretches out, slows down, stretches out, slows down. So where you expect to see it the most is at the turning points, right? Because that's where it's all potential, no kinetic, and so it's sort of just sitting there for, you know, a little bit of time before it starts moving the other direction, right? So what we would expect to see is a pattern where if this is the probabilities, it should be heavily weighted towards the stopping points on either side. Okay, that's what we expect to see just because of our physical model of what we're doing. Okay. So this is integral because there's no imaginary component, and this isn't actually, you know, a function like a derivative or a square root of what's next to it. The operator itself is just a multiplication. Multiplication in this case is not will commute. We can rewrite this as squared x times x, to negative infinity, right? So this would then be, we take this function here, square all the different components, so that would be integral negative infinity, infinity, n of n squared, h, whatever that one is, we're going to square it for, you know, the y component. Oh, and these are all dx. E to the negative y squared over 2 squared. If you take something with an exponent and square it, it's the same thing as taking what's in the exponent and multiplying by 2. So the square here is going to cancel out the 2. Now, within the function, you'll notice that there's no x values. There's y, which is related to x. So it would be actually fairly convenient to switch this from being in terms of x, or sorry, switch the derivative from being in terms of x to being in terms of y. So, we look over here, y is equal to x over a, or x is equal, sorry, not a, alpha. Rearrange that for x, that's alpha y. We have our times x here, so this would be times alpha y. All right, that came from because we were multiplying it by x. Then we got to do our dx. So if we take the derivative of this, right, that would be, let's see, alpha dy, yeah. So dx would be equal to alpha dy. All right, so we can replace this dx with alpha dy. So we got two alphas, those are constants. The n is a constant, so we can move all that outside of the integral.
How about h? Is h a constant?
H is not a constant.
Oh, it's
It is a constant if you select n equals 0. But for n is equal to 1, it has a y in it. And all the ones below that, there's a y component.
So anything with the n above 0 is a function of y.
Yep.
Okay, sorry.
And we're doing a general solution, and so because most of them have a y in there, we're going to keep it inside the integral. Okay, so this is, we can re-represent this as our average x. N is equal alpha squared, and n squared. Just move that side out. Move that outside the integral. Minus y squared times y dy. Okay, so that might look a little bit hairy, but we can actually do something with it. Oh, can actually pull the square out. And squared integral hn e to the minus y over 2. Going back a step. Times y. Y. So essentially, if we take this, what we had here, square it, we get that. Okay. The reason why I went back to this is that okay, in terms of even and odd functions, right? Whether or not it's symmetric about the y-axis, so an even function. We look at our axes, right? Even functions are the ones where, like a parabola here, where your f of x is equal to the f of negative x, right? That's even. Essentially something that's mirrored around the y-axis, right? So whatever you have going this way, you have the mirror image going the other way. Okay. For odd functions, negative x. So an odd function would be like x to the third, or just x. Where up here, it might be plus 2 comma plus 2. And down here, it's negative 2, negative 2. Right? So whatever value you get for y here, when you go plus in the 2 direction, you get the same thing but with the opposite sign. The reason why this matters is if you're taking the integral of an odd function, this area under the curve is a positive value. The area under the curve here is the exact same size but a negative value. So when you integrate from, let's say, negative 2 to 2, you end up with 0. So if we're integrating from negative infinity to infinity for any odd function, you get 0. So for an even function, and let me actually make these different functions. I'm going to use f and g. So if we take the integral of f of x dx from negative infinity to infinity, because it's symmetric, the area under the curve going to the right is the same as the area going to the curve to the left. So this is actually, we can represent this as twice the integral from 0 to infinity of f of x dx. So if we just integrate for the positive direction, we know that the negative direction is the exact same, and so we can just do this. The reason why this is important is sometimes when you're looking in integral tables, the boundaries aren't necessarily plus infinity to minus infinity. Some of them you'll see are 0 to infinity. Those are for the even functions, and so this sort of adds to the values that you can find, right? So if you're trying to take an even function and integrate from negative infinity to infinity, just take what you get from going from 0 to infinity and double it, right? So if you take all the positives, double it, you get all the negatives. For an odd function, because the even side counterbalances the odd side, the integral of all odd functions is 0. So if we can show that this is an odd function, the integral is 0 no matter what. Yes?
I think you drop the square there to the e to the negative y square, won't you? The top function.
Oh, yep.
I was wondering why it's divided by 2.
Because I pulled it back out. So this part here where I canceled it out, I shouldn't necessarily have done. That is for a different thing that we're going to be doing later. Okay? So, even and odd, we get a little bit of board space. So, this part here, some of the properties of odd, even and odd functions. So, an odd function times another odd function is an even. Any even times an even is an even. And an odd times an odd is an odd times an even is odd.
How is odd times odd even? How is odd times odd even?
So let's take just look at an example. So y is an odd function, or I guess, sorry. Let's say our function f of x, right? That's an odd function. If we multiply this by, let's say, g of x, which is x to the third, right? That's also an odd function. If we take f of x times g of x, that's equal to x times x to the third, which is equal x to the fourth.
Okay. So like if you were like just doing, let's say if you let f of x be 7, g of x be 3, that's still an odd.
Not an even and odd number, even and odd function.
So that's like in terms of x's.
So, well, no, it just has to be, it has to depend on whatever axes you're using. If you had 3, right, as your function, if this is your axes, then 3 looks like that. 3 is an even function. It's an odd number, but it's an even function, right? If your function is f of x is equal to 3, it's 3 everywhere. So in the positive x direction and the negative x direction, it's 3, it's symmetric. Okay, I think, oh, and then, so corollary, if you have an odd times an odd times an odd, this part here would be even. So then you'd have even times an odd, which would be an odd, right? Or if you have even times even times even times even is even, so then you'd be multiplying by essentially even by even. So even times even is equal to even. Okay, so if we can show essentially that we have an even function times an odd function, right? And then take the integral of that, because odd times even or even times odd is an odd function, the integral by our rule here would be 0. And so we wouldn't actually have to integrate everything. We just say because it's odd and we're going from negative infinity to positive infinity, it's 0. So, e raised to essentially x, right? Our y is directly proportional to x, right? X is equal to alpha times y. They're directly proportional. There's just some constant between them. So this is essentially e raised to the negative of x squared, right? So in the positive and negative direction, once you take the x and you square it, it's the same value. Right, so this part here is even. H of n, if you look at the tables, that switches between even and odd functions. So you have an odd or even times an even. So this one will switch between even and odd, but we square it, right? So odd function squared is the same as odd times odd. Even function squared is even times even. Both of those give this as being an even function. Right, if you're squaring it, it is either odd times odd, which is even, or even times even, which is even. Right, so as long as you're taking the same function times itself, you're always going to get even. Why? That's odd. Right, so you essentially have even times odd, so that means that the result of this multiplication is odd, So we don't actually care about what all this is. This is an odd function. We're integrated from negative infinity to infinity. Therefore, that's 0. Okay, any questions?
Could you just quickly go over the even part, like just 2 seconds, like how it get even?
How, what's inside of the parentheses is even?
Yeah.
Yeah, so, okay, if whatever's in the parentheses is even, then because you're squaring it, you're taking even times even.
Yeah.
Even times even is an even function.
Yeah.
If it's odd, you're squaring it, so you're taking an odd function times itself, which is also an odd function. Odd times odd is even. So no matter whether what's in here is an even or an odd function, because you're squaring it, the result is even. And so that has to always be even.
So you don't really care what the variables are, right? Like h of n and e, whatever that equals to, whatever. Alright.
Doesn't matter. Yeah, it doesn't matter which, so this one here, e raised to the power, that one's always even. But this one, the Hermite polynomials, if you look through them, some of them are even, some of them are odd, and it actually flips between them with each end. But because you're squaring it, it doesn't matter. So that agrees with our picture of ball on a spring, can compress and extending. Its average position is dead in the middle.
Yeah.
Okay?
For n
Um,
equals what?
hmm?
For n equals what?
No, for any n.
For n. Okay.
And then what differs for n equals 1, 2, 3, 4, 5 is whether this is an even or an odd function. But because we're squaring it, it doesn't matter.
So for any given n, the average value of this is always going to be 0?
Yep. And that's, this little rule here for the integrals can end up saving us a whole bunch. That's actually probably the first thing you should look at. If you can evaluate it, is it an even function? If it's even, integral from negative, and well, you have to be doing either integral from negative infinity to infinity or one value, the negative of a value to the value itself. So if you integrate from like negative 2 to 2, you have to be going from the same place. And if it's an odd function, then it would be 0. It's a nice little rule to
That would be nice to know.
save yourself some serious effort. And otherwise, this is a ton of work to do. Okay?
Yep. And therefore, like, any average of x squared is also 0?
No.
No.
Average of x squared is not 0. Because you have
Oh, it's not y anymore. It's y.
average of x squared would be psi x squared psi, which would be equal essentially psi squared x squared. Well, negative infinity, infinity. So that's n squared n h of n y e to the minus y over 2 squared.
Y squared.
Our x is, we can convert that to y, so that would be alpha squared y squared. Right, so that's alpha y squared, and then you'd have alpha dy. Alpha's a constant, right? So this is essentially alpha cubed and n integral negative infinity to infinity of h n y e to the minus y squared over 2 squared y squared dy. And so this is even, right? And so because this one here is even times even is not 0, it's 2 times going from 0 to infinity. So we would actually have to evaluate it. Yeah?
You forgot the squared on the n,
Now.
and then the dx on the first integral.
Now. Okay, so for that one, we actually have to do the full thing, and
Tables.
no. I'm going to send that one out, because otherwise we won't be doing lab today. And it's probably about an hour-ish or
Duration.
more. Yeah,
Let's do what?
to
Oh my
find
God.
this. It's only a couple lines. Well, it's about a page of derivation.
So we won't be as something to exam.
It would take too
Well,
long.
that makes sense though.
Right.
It's even.
So we essentially have to figure out what this one is. But this one comes out to be a set value. And here, and there, and there. So comes out to be that.
Each bar squared?
Yeah, h bar squared.
Wait, how'd you get? I was just writing down the last line. How'd you get alpha cube? Of that last line, alpha cube n of n squared. Oh, alpha
Squared.
Yeah, alpha squared here, alpha,
Nice down. Okay.
we got 3 of them multiplied by each other. Over here, we only had
Yeah, that's all. That's what we're
2, and so it's alpha squared. Yeah. So I'll send out the derivation for it. It's using those properties of the Hermite polynomials to do not as fussed about you guys, knowing that in particular. Essentially, one of the big things I wanted to get out of this is that concept of even and odd functions. That really helps out with a lot of the integrals. Essentially,
Can you make an integral odd somehow?
Hmm?
Can you make an integral odd somehow? Like just make that odd so it's zero?
Well, it has to make physical sense, right? So, for what we were doing, right, the average position, because half of the time it spends in the positive direction, half the time it's in the negative direction, the actual function itself is odd. Well, that function itself is even, but when you, here when you're finding the average, because you're multiplying it by x before taking the integral, right, that becomes an odd function, and so the average value is 0. So physically it makes sense that it's 0. For the x squared, right, we were saying that it's going to be highest probability around the turning points, right? And because it's squared, it's looking how much is the displacement. And so we know that it's not, on average, going to be in the middle, it's more towards the edge. So that one is not going to come out to be 0, and so we expect to actually have to integrate and come up with some number. Okay. Okay, so the ramifications of this, right? If we plug in 0, and I already erased the energy for that. Should we get this right? Back one slide. There we go. Our energy is this right here. All right, so this is our energy term. If we plug in a 0 for n, that's 0. That's 1/2 h nu, and then nu is kf over mu. Mu is your reduced mass, right? Which means we can have an n equals 0, but the energy is not 0 there, right? If you plug in a 0 for n, the ground state, the resulting value is not a 0 energy. Right, and that makes sense from the Heisenberg uncertainty principle. If the energy was 0, it would be stationary, right? And so you'd have an exact position and an exact velocity, which we can't have. Okay, so the difference between our modeled system down here, right? The difference between our modeled system and the height of the first energy, that value is called the 0-point energy, right? It's the energy at 0. A lot of times it's ZPE. When you're doing a calculation, if you look in there, it has a value that says ZPE equals, gives you a number. That's what the number is, right? It's the amount of energy stored in the 0 in the ground state.
So
So
if you were to ask us like, hey, find the energy difference between n equals 4 and n equals 0, we would just use the ZBE value for 0 and just find the value calculated for 4 and subtract.
oh yeah, well yeah, what you do is going back to this equation, take this, plug in for 4, minus plug in for 0. So essentially, yes, you take the ZPE, but you know, you do 4, take this, plug in 4, take that, plug in 0. The difference between the two, that would be the amount of energy needed to excite it up to the 4th level. We're actually going to be doing something like that today, except not with a harmonic oscillator. We're going to be doing that with the particle in a box. But the same concept works. If you're trying to figure out the difference between energy levels, you plug the n for whichever energy level you're interested in, and then the other one, subtract the difference between the two e's, and then it's either that's the energy of the photon that comes off, if you're talking about, you know, a relaxation from the higher to the lower, or that's the energy of the photon that's required to kick the electron up, depending on directionality. Okay. If we map out the function, the number of nodes in your vibrational modes is is equal to your n value. So at 0, there are 0 nodes. At 1, there's 1 node. 2, there's 2 nodes. At 3, there's 3. 4, there's 4. 5, there's 5. Okay, so the number of nodes is equal to your, in your book, the new value. I prefer just using n when it makes sense.
When was it before, like when it was like n minus 1? You know, the number of nodes was always like n minus 1? We had that discussion.
That was for particle in a box.
Okay.
Yeah, and that's because your particle in a box n equals 1 was that one. So for that one, it's n minus 1. Okay. If you take the functions the wave functions and you square them, the resulting displacement follows what we think it would, which is the curves are highest on the two sides, right? Which suggests that it's the probability of finding it is higher at the turning points than at the middle, which is agrees with our idea that it's, you model it based on the spring, where the spring is traveling through the center really fast, and so it has a low probability of finding it there. It's going to have a higher probability at the two turning points where it's all potential, no kinetic, as it turns around to turn that potential into kinetic energy. The big thing from this particular one that I want you to get is, this part here, the even versus the odds. That's going to help out a lot with other stuff. And then to know when we're talking about a Hermite polynomial, that's what we use for the harmonic oscillator. Any questions? No? Okay, we will be doing particle on a ring next week. And so we will actually finish up the material for the exam next week. Okay?
That's the last concept, particle in a ring.
Particle in a sphere is the last one, but it's related to particle in a ring. It's particle in a ring, we use that to build up. Particle in a ring is going like this, so it will be used for like benzene or substances like that, and then we can think of particle in a sphere, which is take your particle in a ring and then just spin it. So we can use particle in a ring to go particle in a sphere. Okay?
And that's, when they go on,